Hello everyone, my name is Rishit Kumar and ID number is 19001477 and I am from Group Integrated Project 1K. So today I'm going to talk about the diagram we designed for our integrated project. So the first one is the diagram. In the diagram we have combustion chamber, gas turbine, steam turbine, condenser, heat exchanger, pump and compressor. When Q in enter into combustion chamber, it flows through gas turbine and heat exchanger. Heat exchanger then flow through the compressor, which produce V in compressor. And then the heat exchanger will flow through to the heat exchanger will flow through to the steam turbine. And then the steam turbine will flow to the condenser, which is Q out, and the condenser will be the flow through the pump, which will the last of the mechanism. So the explanation for our design is, in the plant there are one compressor, one compression chamber, 6 turbine, one generator and one pump. The gas turbine as a compressor where the engine collects ambient air. The compressed gas is combined with such a hydrogen fuel and then mixture is burned. The hot air is produced will pass through turbine blades and allow the turbine to spin. The turbine has an isentropic expansion. In the condenser, constant pressure heat rejection process occurs. So now we're going to talk about the process of the design, what we do in our integrated project. So we have only two cycles, which is Rankine cycle and Brayton cycle. The power plant operates in a Rankine cycle for steam turbine, while in Brayton cycle for gas turbine. Rankine cycle can handle the isentropic compression, which involving two phases of working fluid, and the steam produced by Rankine cycle with higher quality. The Rankine cyclic method is used to analyze and measure the steam power plant. This thermodynamic cyclic approach defines the conversion of thermal energy into mechanical energy and vice versa. Brayton cycle is work based on a thermodynamic cycle using constant pressure, heat and rejection. Fuel and compressor are used to heat and increase the pressure of a gas. The gas expands and spins the blades of the turbine, which when connected to a generator generates electricity. Thank you.
Now is the calculation part. Here is the data that we got from manual calculation. For backwork ratio of combined cycle, the equation we use is BWR is equal to W in over W out. Since W in is equal to W pump plus W compressor, and W out is equal to W gas turbine plus W steam turbine, the BWR is 0.04. The lower the backward ratio, the better of the performance of combined gas steam cycle. Next is overall thermal efficiency. We use this equation, which is eta, or efficiency, is equal to 1 minus QL over QH, or Q out over Q in. Thus, the thermal efficiency is 0.612 or 61.2%.
Next, for coal required, low sulfur grade coal is a subbituminous coal, and the heating value of subbituminous coal is from 17.4 to 23.9 megajoule per kilogram. Assume that the heating value equals to 23 megajoule per kilogram. By using this formula, we can get that the mass of coal required, which is 2131.2 kilogram per minute. Then, for the steam generated, we will be using this formula to calculate the steam generated by multiplying the mass flow rate of the steam and the specific volume of the steam. So here, the specific volume of the steam is equals to 0.013654 meter cube per kilogram. Then, we will get the steam generated, which is 2.26 meter cube per second. Last but not least, for the actual power, the energy balance for combined gas system power cycle will be shown as here. From the energy balance, we can get that Q net in or heat transfer net inlet is equal to 500 megawatt, which is also equals to the W net out, which is work done net outlet. Hence, the actual power produced is equal to the work net out, which is 500 megawatt.
Within the gas steam power station, there are four main components: the pump, condenser, boiler, and turbine. There are a few methods that can be implemented to improve the gas steam power cycle. To improve the cycle, we can look at each component individually. First, the boiler. Within the boiler, we can increase the pressure of inlet as to increase the temperature of outlet steam. Additionally, the steam can be superheated to even greater temperatures with a higher efficiency boiler. Following this, the temperature of steam that reaches the turbine is at greater heights. Secondly, the condenser. This component is responsible for converting steam that leaves the turbine back to condensed and cooled liquid state. By lowering the condenser pressure, we can increase the overall work output. To make sense of these improvements, a graph of TS diagram can be used to show the overall work output. Additional steps can be taken to improve the overall design of the cycle.
Hi, my name is Elia Shahira from CE1 with ID 1900-1104. We'll present the conclusion of our Thermodynamics integrated project. For this integrated project, the members are to use sources available to determine the amount of coal required, steam generated, actual power produced, number of turbines, generators, pumps, heat exchangers, and support equipment and type of cycle model. In the plant, there are one compressor, one combustion chamber, 6 turbines, one generator, one pump, and one shell and tube heat exchanger, and also one condenser. For this project, air was used as the working fluid for gas turbine cycle and considered as ideal gas, and water was used as the working fluid for the steam turbine cycle and acts as the cooling medium. Conclusively, for the cycle, the steam turbine uses Rankine cycle while the gas turbine uses Brayton cycle for this integrated project.